Hi, everyone. My name is Alexandru Burdusel. I'm a PhD student from King's College London. And in this presentation, I'm going to talk about some of the work that I've done over the past few years. I'm almost done with my PhD now. My research interests are model-driven engineering, optimization methods, and combining the two together with domain expertise from various domains, not just program repair, so that we find better solutions to existing problems that domain experts may have. While this work doesn't specifically focus on program repair, it has a broader application scope. I'm just going to briefly describe the signature of the type of framework that I'm going to describe today. So typically, in most cases, we have a domain expert who are familiar with, let's say, a specific domain, let's say engineering or software engineering. So in that case, the domain expert is a software developer. And they may have a problem that can be classified as an optimization problem. They don't necessarily know much about optimization. So the goal of our work is to abstract away the optimization knowledge from the requirements of the domain expert and just let them to specify the problem, apply it using a set of optimization algorithms and an optimization pipeline, and then just get back some optimal solution models at the end so that they can decide which one best suits their needs. So typically, optimization problems have this common signature where you have a set of control variables. So these are things that are changeable, which give you a lot of options to pick from. And you don't necessarily know which one is the best one to choose. Then you have a set of constraints. These are boundaries that limit the intervals for the options that you have to choose from. And then you have a set of guidance functions. So a guidance function or an objective function will indicate how good a solution is given the values you've picked for the control variables and whether the constraints that you've specified are satisfied or not. Typically, when a constraint is invalid, any objective function value is also not valid. So some examples are, for example, architecture refactoring, program repair, process improvement, also component deployment when we seek to minimize the use of resources in the cloud. This framework can be applied to any number of fields, not just software engineering. So going back to the description of our approach, to add a bit more detail, the domain expert will have to specify what the solutions they're looking for look like. So they use their domain expertise to create a type of language that they can specify with our framework. Then they add a set of constraints. They indicate what makes a solution good. And they also specify how to modify the control variables so that the solution search space is explored with the help of the guidance functions that he has specified. And hopefully, at the end, if everything is done correctly, the optimization tool that they use will return some optimal solution models. So to look at this in a bit more depth, the search space of a problem is formed of the domain, the changeable domain subset, the constraints, and the objective functions. So this is typically what is specific to any optimization problem. And then a concrete instance of such a specification gives us a problem model, as we call it. And then we take this model and we apply a search algorithm over it using a specific translation from the problem to the tool, to the language understood by the tool. We apply evolutionary search over this problem model, and then hopefully at the end we get some optimal solutions. So I'm going to look at an example of an optimization problem. It's not from the program repair domain, and this is on purpose. This is to emphasize how this approach can be used on other fields as well, not just program repair. So an example, at KCL, undergraduates have to develop a final year project at the end of the year. And these projects are advertised by a number of academics. And each academic will say, OK, I have a number of projects. And then students apply for implementing one of those projects. And then at the end, academics have to form teams so that they evaluate the students. So typically, a team consists of 3 markers. The first marker is the project supervisor. The second one is allocated by someone. And then the third marker is just someone who oversees that the first 2 markers agree on a grade, or if they don't, they will try to steer the discussion so that at the end they will reach consensus. So the goal is to find the best team allocation distribution for the supervisors so that we minimize the number of teams. Also, at the same time, we want to reduce the load that all the supervisors have to do. So we don't want to have someone who supervises, let's say, 15 projects, and then someone else who supervises 5. We want that number to be equally distributed. Finally, we want to have teams that have at least 3 members, but not more than 5 academics assigned to them. So to look at how we specify this using a class diagram, I've created a simple UML class diagram. So as you can see here, we have the main model that contains a class of type academic. And then we have a class of type project, class of type student. Each student is assigned to a project. And then each project has a supervisor, and then a first marker, which is the same person as the supervisor. And then we have to identify the second and the third marker. So looking at this class diagram and taking into account the goals that define our optimization problem, this is the changeable syntax subset. So this is what should change in model instances so that we can find the best, so that we can try to find the best solutions for this problem, keeping in mind the goals that I've specified earlier. And in our approach, the way in which we do this is by using a visual language that allows us to consistently make changes to a class diagram. And this is based on something that's called graph transformations. So these visual rules will be applied to model instances of the class diagram that we've seen earlier. And the different colors indicate the type of changes and the pattern that needs to be present so that we can apply the change. So for example, in this case, we assign a second marker. So we want to create the edges between an academic and a project. But we can only do this when that project doesn't already have a second marker. And also, we don't want to assign a second marker from an academic that's already the supervisor of that project. And the same idea applies to the other two transformation rules that I've included. These diagrams are specified using a language that's called Henshin. As I've said, it's based on graph transformations, and it allows us to specify any type of changes to a class diagram. So moving on, from the class diagram that I've described earlier, we can also automatically generate code so that we can implement our goals using this approach. So an example objective function, can everyone see this? So an example objective function that uses the automatically generated code looks something like this. So we have an instance of the marker allocation model. And from here, we count how many projects have a complete marking team. So this, by including this slide in my presentation, I just want to highlight that this approach makes it easy to work with problems that can be specified in any domain. So using a classical optimization tool, let's say something like Minizinc, which is a constraint solving language that allows you to use several solvers to solve these problems, you'd have to manually create an encoding of your problem in the Minizinc language, solve it in Minizinc, which requires some optimization knowledge. And then once you get the solutions, you'd have to translate those solutions back into perhaps an instance of some Java code, and then you'll have to use that Java code to generate the solutions in the format that you desire. This approach abstracts away the requirement to have to know much about optimization, and you also don't have to do the parsing between the Minizinc artifacts and the artifacts that you would need the solutions to your problem. Sorry, and the artifacts in which you would need the final output of the problem in. So to put it all together, once we've specified the class diagram, the objective functions, how we change the elements of the class diagram, this is an example of the language that we've built to allow you to specify problems. And this is part of a tool that we call MDEOptimiser. And here we have several blocks that split the various parts of the optimization problem for your domain. So in the first block, we specify the problem using the meta model. So this is the class diagram and the specific instance of it. So this is defined by the meta model keyword here, and then the model keyword here, which is pointing to an instance of the class diagram. And then we have the specified goals that we've implemented using the automatically generated code from the class diagram. So we have two objectives. The first one is to minimize the number of marking teams, and the second one is to minimize the average marker load so that there's no variation between the number of projects that all the markers have to mark. And then we have the 3 constraints as we specified on the problem spec slide. And then in the search block, we specified the 3 model transformations that allow us to make the changes on the class diagram. And then finally, we have some details about the solver to use. In this case, I've included the NSJ2 algorithm with some additional parameters like the population, the type of mutation to use, and for how long to run the search in this instance. For a closer look at how this works, we take all the inputs from the user, and then behind the scenes, we use an evolutionary search. So we initialize the population. We generate new candidates by applying the transformations to model instances that are copies of the initial problem model that's applied by the user. And we do this for a number of steps by using the specified search algorithm. And hopefully, if everything has been specified correctly, at the end, we get some results. One key aspect of this approach is that this approach, in this work, we run the search directly over the models. So unlike other approaches where you would have to translate your model to, let's say, a binary encoding, so 1s and 0s, and there you'd have to flip the 1s and 0s, take the newly obtained binary string, convert that back to your solution, see whether the solution is better or worse than the previous one. In this approach, we don't have to do that step anymore. We just change the model consistently right away, and then we query it using the implemented guidance functions, such as the objectives and the constraints, and we are able to quickly see whether a newly generated model is better or worse than its parent. In addition to this, we have another language that allows you to run this type of search at scale. We're calling this language MDEOscale. So basically what it is an optimization orchestration framework that allows you to specify a number of problems. For example, if you have multiple tools that you want to compare the outputs of, or if you have the same tool but with different parameters, you can specify them using this language, and then it will allow you to run your search on Amazon Web Services. At the moment, only Amazon Web Services is supported as a cloud provider, but this can be easily extended to other clouds. And the benefits of this approach is that typically, I don't know, at least in my case, when I was doing experiments, sometimes I would have to run search on my laptop for days on end. With this approach, I can quickly scale up the experimentation phase of any paper and get the results maybe in a couple of hours. Well, I don't know, running experiments that would be the equivalent of running the same thing for 2-3 months on my laptop. Also, another benefit of this tool is that it allows you to see some statistics at the end of a run. So it will automatically generate some charts, and also it will run some summary statistics on the results that have been obtained. as you can see, it also generates Pareto fronts that allow you to compare the sets of results obtained by two tools. For example, here, the blue dots show one tool, and the green dots show another tool. And here, it shows how the search progresses over time for, again, two tools. And here, the dip shows that initially, there are no valid solutions because objectives default to 0 while the constraints are being dealt with. But once the constraints have been, once the search found solutions that satisfy the constraints, immediately the objective values are taken into consideration, and this gives us this peak in the chart. Okay, so this brings us to the conclusion from my talk, but I want to also maybe show a quick demo of the tool. So to summarize, we call this approach search-based model engineering, and the aim of this is to make it easier for domain experts to run search for their domain-specific problems. And another benefit of this approach is that this tool, MDEOptimiser, allows you to run the search directly over models. So this can be an instance of the code or a model that's derived from another process that has an optimization problem which needs to be solved. So quickly, to have a look at a demo of the tool. So I have here an instance of the case study that I've described. And this is running as a plugin for the Eclipse IDE, but the tool can also be executed in a headless mode from the command line. So here we have the language that we've also seen on the slides. And I'm not going to run the experiment here, but once we run it, the tool produces some outputs that give us some indication about the quality of the solutions it has been able to find for the specified problem. And without using the MDEOscale tool, it also generates some charts, such as the Pareto front chart, if there's more than one objective for the problem being specified. In this case, there's only two solutions that have been found for this case study. So we see that for one of them, we have 47 teams and a variation of 0.63 projects between the markers, and another one that has one more team, but a smaller variation of projects that are marked by supervisors. Also, the tool generates some granular data that can be used for analysis with other tools or languages such as R or Python. I think this concludes my talk. Thank you very much for your attention, and I would be happy to take any questions.
No questions? Good then.
Okay.
Well, let me just grab the stage for a second. So thanks for staying with us until now. Thanks, Alex, for your presentation. If anyone wants to stay around a little more, we are going for a friendly pint at the Crafts Beer & Co. as announced it before. So stay around if you want, and we'll continue the chat maybe. Thanks very much for coming.